Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Well, at this point, we've completed our schematic and we're confident in our design. Now we've come to the point where we're ready to create our own PCB. In this video, I'm going to present the basic of PCB design. Now, there is a lot more to learn beyond what I'm going to be covering here, but what you will learn here is enough for the average experimenter to get a foothold up to begin their own awesome designs. In the next video, we will be actually walking through the design of a PCB that we'll create for our mixer project. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, we begin our discussion by answering the question, what is the anatomy of a printed circuit board? We begin this discussion by addressing the whole topic of the cross-section of a PC board. To do this, we're going to slice a PC board and look at it from the side view to see what it is composed of as we move from the top of the board to the bottom of the board. In its most simplified version, the first thing that we come to is what is called the substrate. This is an insulating material which can be one of many things, and one of the most common substrates is a fiberglass material called FR4. The term FR4 refers to a family of fiberglass materials used for this purpose. Adhered to the bottom of this substrate is a layer of copper. This copper can be of various thicknesses. This thickness is expressed in ounces. The most common thickness is 1 ounce. So what do they mean by 1 ounce copper thickness? Well, this refers to 1 ounce of copper spread evenly over 1 square foot of substrate. There are tables available online which equate actual copper thickness in thousandths of an inch or in millimeters to this ounce nomenclature. Knowing this thickness is an important part of designing certain PCB features which we're not going to discuss here. The copper adhered to the bottom of this substrate is referred to as a layer. With just a single layer of copper adhered to the substrate, this is a single layer board. Now, let's add some more complexity to this by putting another layer of copper on the top of the board. So now we have a layer of copper on the top and a layer of copper on the bottom, forming a 2-layer PC board. The most common overall thickness for a PCB is 0.062 inches or 1.57 millimeters. Now, let's go the next step. Suppose we have a lot more signals and power and stuff and things that we need to ship all around the board, and we're just running out of routing space on the 2 layers. So what do we do now? Well, we take two 2-layer PC boards and we glue them together, one on top of the other, with an insulating material between the 2 boards. This insulating material is called a pre-preg layer. Now, as you can probably guess, this would make for a very thick board because we would have 2 times 0.062 plus the thickness of the pre-preg layer. The reality is the finished board is still only 0.062 inches thick because they use a thinner substrate materials for the 2-layer boards. Now we have a 4-layer board, and this exact same process can be performed again and again and again to create many, many multiple layer boards. I personally have designed up to an 8-layer board. Now that we have all the copper in place, let's talk about the next layer, which lays on top of the copper on the outer layers of the board. Well, these PC boards are run through an automated process to solder parts onto them. Originally, this was a process called wave soldering. The populated boards were placed on a conveyor belt with the bottoms of the board would ride along the conveyor belt with their bottom laid into a vat of molten solder. The solder would wick up into the board and all the parts would be soldered in place. The problem that they had was that solder bridges would form between pads and traces that were close to one another on the board, right across the substrate. So to fix this problem, an additional layer was added to the boards that is called the solder mask. The purpose of this solder mask is to put up roadblocks to solder bridges. The solder mask has openings in it called apertures, which allow the solder to get to the stuff that needs to be soldered. Now, while this solder mask could be any color they want it to be, the most common color is green. OSH Park, my PCB supplier of choice, uses a purple solder mask. Thus, their motto, perfect purple PCBs promptly. Well, with modern boards, we have surface mount parts, and the need for the solder mask is still there. With this process, a small dot of solder impregnated paste is daubed onto each place a part is to reside. The parts are all placed on the board by a robotic pick-and-place machine. The fully populated boards are then passed through an oven. The solder in the paste melts. The parts self-center and settle into place with a bead of solder on each pin. This process is called the reflow process. Well, we're not done yet. We still have one more layer to talk about. Well, I suppose that you've seen PC boards before and noticed the white lettering in various places. This white lettering identifies component reference designators, the position and orientation of components, board identifiers, part numbers, manufacturer names, what connectors are for, and, well, a whole bunch of other things. This text forms one more opportunity to provide documentation which is manufactured into the board and costs absolutely nothing more than to add additional features of this type to make the board easier for assembly and troubleshooting. This text is all traditionally created in the PCB design software, and it is used to create a silkscreen which they lay over the board, then squeegee white epoxy ink onto. The ink passes through the silkscreen in the open spots, placing the text on the board. Because of the process used, this white text we see is called the silkscreen layer. Like the solder mask, it only resides on the outside of the board. Now that we understand the cross-section of the board, let's turn our attention to the connections that are made on the board. Well, our board is a very physical entity and must exist within some sort of physical world defined by the enclosure and its various electrical and mechanical interfaces to the world around it. We define the extents of a PC board by defining what is called the board outline. This is dictated by its final resting place in the enclosure. All of the parts associated with the board and the connections between these parts must exist within the confines of this board outline. Like the PC board itself, the parts we put on the PC board and that appear in our schematic are very physical entities. Each of these parts consume physical board space and have physical pins in specific locations. Some of the parts must be oriented in a very specific way for them to operate properly. All of these physical realities are baked into what are called the PCB patterns or footprints. All of the parts are then arranged on the surface of the PC board. But how do we connect the pins of all these parts per the dictates of the schematic design? Well, we have defined the extents of our PC board by defining the board outline. And we have placed all of our parts within this outline in a way that makes sense. The first thing that we see are these funky blue lines everywhere. What are these things all about? Well, each one of these blue lines represents a connection that the schematic requires that has not yet been made. Because it is such a total mess of lines, they're called ratlines, kind of like, it's a real rat's nest. These can help you envision the way that traces will have to go to get to their destination. It also helps to orient the parts in the board. Each time you complete a required connection, its associated ratline will disappear. So how do I complete a connection? Well, there are two ways to connect things together on a PC board. Both are very common and each has their own distinct purpose in life. The first is laying down copper lines between one component pin and another. These lines are called signal traces, or just traces for short. Traces have a specific width, which is determined by the kind of signal passing through it. Low current traces can be very narrow. But with that said, there is a limit to how narrow the traces can be and still have an affordable board. When trace widths get narrower and narrower, the number of PC board fabricators who will produce the board will go down, and the boards get more and more expensive to produce. If you stick with dip traces, default 13 mil, which is 0.013 inches, trace width for normal low current traces, then you'll be good to go everywhere. If your trace is going to be carrying any kind of current, then the trace width has to be increased accordingly. The actual needed width depends on the current to be carried, the allowed temperature rise of the trace, the overall length of the trace, and the copper weight of the board, such as 1 ounce copper versus 2 ounce copper. And there are online calculators available to determine this number for you. I've put a link to one such calculator in the description for you. But I did say that there are two ways to connect things together, and so far I've only told you one. So what is this second way? Well, the second way we connect things together is using what is called a copper pour. Copper pours are generally used only for things like the board's ground and or power plane, and are generally the last thing placed in the board. Ground planes generally live on the outside of the board, the top and bottom layers. If there is a power plane, it usually lives on one of the inner layers. This avoids some accidental shorts to the power supply. Now, with that said, we can use copper pours to make what amounts to be very, very large traces for high current devices, or maybe heat spreading copper for the heat generating devices such as power regulators or transistors. When a copper pour, which is associated with a particular signal, power or ground, is poured around a component pin which is of the same signal or power or ground, dip trace automatically connects that pin to the copper pour or plane. It does this in one of two ways. There can be a direct connection, which means that the pin is assimilated into the copper pour and becomes indistinguishable from the plane. This is not a bad thing when we're talking about the vias used to connect the planes and various layers together, well, because there's no soldering involved. On the other hand, if you're trying to solder the component in place, the entire copper pour acts like a huge heat sink, making it very difficult to make good solder connections. And this is not such a good thing. Usually component pins are connected to the plane using spokes. These are very short, relatively narrow traces that connect the pin to the plane. They act as a thermal relief, making soldering more possible. Their impedance is very low, so that they really don't affect the function of the circuit in most cases. Now, the last thing I have to address regarding copper pours are the areas of disconnection between parts of the plane due to traces. So you have this board with various traces running all over the place and signals and all this kind of stuff, and then you place your copper pour over the whole layer for a ground plane. It is possible that the placed traces will create areas of copper pour that are not connected to the rest of the copper pour. This means that while they're technically part of, say, the ground net of the board, they're actually not electrically connected to one another. These are called islands. So when we finalize the layout of the PC board, we need to discover these islands and take steps to allow the pour to be electrically connected to itself everywhere. This can be as easy as moving a trace or jumping a signal to another layer. Sometimes this is an impossibility, and we rely on a connection to its cousin plane on the other side of the board to make that connection. Now, we have signals living on traces on the various layers of the board. So how do we get a signal from one layer to another layer? A via, or static vias as DipTrace calls them, is a plated through hole that exists between layers on the PC board. These carry signals, power, and ground from one layer to another. There are three basic kinds of vias that are used. There's the through via, there is the blind via, and there is the captured via. A through via goes from the top of the board through all of the layers all the way to the bottom of the board. And these are the most common style of vias. They can use to systematically connect the ground plane on the top of the board to the ground plane on the bottom of the board so that they both remain at the same potential everywhere. The next two kinds of vias are only used on boards sporting 4 or more layers. Blind vias go from an outer layer of the board to an inner layer and stops there. Kind of like a blind alley. There's an entrance but no exit. Captured vias go from one inner layer to another inner layer. These are totally hidden from sight as we look at the board from the outside. As a general rule, avoid using blind and captured vias whenever and wherever possible. Among other things, they drive up the cost and the complexity of the board. Well, the last thing I need to address is the spacing of things. So now we have all of this copper on the board. We have traces, we have copper pores, we have component pins, we have vias. How close can they be to one another? Well, there are limits. And yes, you can have things very, very, very close to one another, but at a cost. Clearances on a PC board define the distances that are allowed between traces and vias, between copper pores and traces, between copper pores and the edge of the board, and, well, a whole lot more. And all of these things are defined in what are called the design rules. While you can make them whatever you want them to be, generally it is a good thing just to use DipTrace's defaults, as these work for most board fabricators. With that said, if a particular signal or power trace requires something other than the default settings, you can define all of the special default parameters for a given net on a PC board, which include things like the trace width and the clearances and all kinds of stuff. And this is an absolute must if you're going to use an auto router. Then there are the places you just plain don't want stuff to reside. Suppose there were areas on the board that you want to be sure that no components exist. You can define this area with a component keepout. On the other hand, maybe there are places that you don't want any copper to exist. This could be copper traces or copper pores or any other such thing like that. Then you would draw a route keepout area. These two keepout areas can be defined for a single layer or multiple layers or for all of the layers. And this is specified in the keepouts properties. Now, we also need ways to mount the board to something. How do we do that? Well, we can't forget this thing, and it is very easy to do. We can get so wrapped up in placing parts and routing traces and putting on copper pores, and then we come up for air at the end and say something like, oh yeah, how am I going to mount this to the enclosure? Oops, now what? Then we scramble trying to find places to stick mounting holes with enough clearance to allow for hardware without shorting against traces and stuff. The good news is that DipTrace has ready-made method for placing mounting holes where you define the hole diameter and the keep out around it, and all you have to do is drop them where you want them. Now, while I am addressing this last, it actually should be one of the very first things that you place on the board. Well, admittedly, this isn't everything that there is to know about PC board design. There is a ton more stuff about PC board design that I haven't even touched on yet. But this is the foundation you need to start creating your own boards. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.